Hello dear students, you must have remembered that in the last class we have introduced to you some basic boolean operations such as the or, and the not. I know that you are definitely familiar with this type of operation from your higher secondary classes, and this was just a recapitulation for you. In the today's class also, the first half of the class will be basically a recapitulation of your earlier knowledges that you have learned. This will definitely help you and it will be a brush up for you. Today we will start with the NOR and the NAND logics that you are also accustomed from your higher secondary days. But just for the sake of completeness, I need to discuss about all of them, and so here we start about the NOR logic first of all. So it's the NOR, and I call it operation, NOR operation. So first of all I will go for the NOR operation. Just give me a minute. Okay, that's fine. So first of all I will be discussing about the NOR operation. So as the name suggests over here, that it will be just the complementary of the OR operation. So what was my OR operation? So the OR truth table, as if you remember, so the truth table of this NOR operation will be NOR operation. So this is the truth table of NOR operation. Let me show you. So suppose I have an input. First of all I bifurcate the sheet into two columns, that is the input and the output. So this is my input and output, right? And now in this input and outputs, whatever I am going to do is, I have two inputs, that is A and B, although NOR gate can be multiple inputs just like the OR gate. And in the output, first of all I write over here Y. This Y is my simply A or B, right? And then I also write this Y bar. So this one is nothing but the NOR operation over here. So Y bar is equals to the NOR operation, because you know that this Y is equals to A plus B. The actual pronunciation is A or B, as I have said you in the last class. So this one is your OR operation, and then comes the NOR operation over here. So actually what I am going to do over here, you know that the possibilities are 0, 0. You may write high low also. I am showing you all the possibilities. In the last class I have shown you high low, that combination. Today I will show you the 0, 1 combination. You can use any one of them. The next combination was 0, 1. The next will be 1, 0. You see that I am just gradually increasing the binary number by 1 bit each and every time. So 0, 0, 0, 1, 1, 0 and 1, 1. So according to OR operation, you know that if any one of the operation, if A or B, any one of them is high, so then the output will be high. So that is why the output looks like this, and just basically in the NOR operation this will be complemented. So you see that the output is just the complement of the OR operation. So that is what we find in this particular approach, that it is just a simply complement of the OR operation. Now if I just want to put it, so it is like this, it is A plus B and then A complement. So this is nothing but the NOR operation that we find over here. So this one we can call it, safely we can call it the NOR operation, right? This is the NOR. This is the NOR logic. And if you want to put it in the logic gate representation of this one, so if you want to put the circuit of this one, as you know the circuit of OR gate, I have shown you in the last class, you also know it. So this is the circuit of the OR gate, and then you should put a NOT gate in front of it. So that gives you a NOR operation. So this is simply Y equals to A plus B and then A complement. Roughly speaking I will call it A plus B, but truly speaking it is not A plus B, but rather it is A or B. So this one is my input A and this one is my input B. If I have more number of inputs, A plus B plus C, so that can be also possible. And the simplified logic symbol of this one is, simply you draw an OR gate You simply draw an OR gate and you put a circle or a bubble in front of the OR gate. So just you put a bubble in front of the OR gate and that will give you see these left bubbles that I am drawing, a left edge bubble gulo draw korchi. This has no particular meaning, okay, this has nothing to do with complement, these are just for designing, but this bubble is very important and this bubble actually signifies the NOT operation, that is the system is complemented. So this one is your Y. So Y is equals to, once again it is A plus B and then a complement. So this will be the symbol of the NOR gate, so that I will be using. So this one is the NOR logic gate. This one is the NOR logic gate. So NOR is nothing but the complement of the OR operation, and it has some fundamental advantages that I will be also discussing with you. I think that this one will be also a recapitulation for you. You have learnt in the higher secondary classes that NOR and NAND gates can be used as universal gates. Universal gates means from this NOR and NAND gate, if you have in your laboratory a NOR gate, then you can make all the logics by using this particular gate. You have also a practical, a laboratory practical on this issue, that you need to show practically that a NOR gate really acts as a universal gate. So you have it in your practical class and you will definitely do it. Next I move on to the NAND operation. So the NAND operation is something like this. So this one is called the NAND operation. So next we go to the NAND operation. Right, so this is my NAND operation now. So what is the NAND operation? NAND operation is nothing but the complement of your AND operation. So the logic is Y is equals to A and B complement. So the logic is simply A and B complement. So this is nothing but the, we can call it safely that complement of AND operation. You can call it complement of AND operation. In the previous one also you please add this complement of OR operation. So this one is safely complement of AND operation. So this is what I have understood very well, that Y is equals to A complement B. Okay. So now if I go for the truth table of this particular system, so then I should write that truth table. So if I write the truth table over here, that should be, let me make the box. Okay, so it is made. So I bifurcate into my input and output. So suppose this side is my input and this one is my output, and then whatever I can do is my two inputs are A and B and my outputs are Y and then Y complement, and here I write that Y is nothing but A and B and Y complement is my NAND operation. Okay, so I am interested in my Y complement. So if I put over here this one 0 0, then 0 1, then 1 0 and 1 1. As you know that in AND operation, that when A and B both are high, then only I call it high. So when A and B both are high, then only I call it high. So that is 1, and similarly all others will be 0 over here. So you see that all others are 0 and the output will be complemented. So just you get the complement over here. So that's the simple NAND operation over here, and the logic symbol of this NAND operation, that is also very much clear to us, because if this is my AND operation, so this is my AND operation, you know, then that AND operation in front of it you should put a NOT gate, and that will basically give you a NAND operation. So you may just put it A B, and here you will get it Y equals to definitely A and B from the AND gate and then a complement. So this is what you have from your AND gate, or this one can be simply simplified to, you just put a bubble in front of it, that is sufficient to indicate that this one is a, and this one is a NAND gate. So this is A and this is B. So this is simply A equals to A and B complement. Okay. So I think that you are definitely familiar with these particular issues that I have discussed with you so far, and now I will move on to another gate that will be of some other importance also to us. So let us now move on to that particular issues. Just give me a minute, I need to find it. So this one will be the XOR gate. I would also like to discuss the XOR gate with you at this moment only. Although XOR gate is not too much required by us at this particular instant, but still I will be discussing the XOR gate with you. So I will be discussing both the XOR and the XNOR gate with you. So let me now show you about the XOR and the XNOR gates. Okay. Yeah. Now I will show you about the XOR oblique X NOR. XOR oblique X NOR. So this is our next item of discussion, that is XOR or the XNOR gate. So what are XOR and what are XNOR? So if you have read it earlier, that's fine, and if you didn't, so then I will be discussing again about the XOR and the XNOR items. So what is XOR and what is XNOR? So let me show you. First of all, I will show you the truth table of this particular gate. I write y1 and y2. y1 corresponds to XOR. y1 corresponds to XOR and y2 will correspond to XNOR. y1 corresponds to XOR and y2 will correspond to XNOR. So now let me show you that what are the XOR and the XNOR operations. Right. Okay, so here I start now. So the inputs will be as before only. So the inputs will be as before. I will take my inputs to be this 0 0. This is one of them will be 0 1, then 1 0, and finally 1 1. Now in the XOR, the output is simply this one is 0, okay, 0 1 1. Okay, this is 0 1 1, and then it will be 0. That's simple. So it is like this. And you also have to know that y2 is nothing but the complement of y1. XOR and XNOR. Etar puro kotha hoche exclusive OR gate and exclusive NOR gate. I repeat, exclusive OR gate and exclusive NOR gate. Right. So OR and NOR, you know the relation. OR or NOR er moddhe relation ta ki ache. So between OR and NOR, you know the relation, that is simply complement. Okay. So OR and NOR, the relation is very simple and it is just a complement of each other. So that is what is going on, that y2 is equals to y1 complement. So that is why you can definitely write over here 1 0 0 and then a 1. So this is what is exclusive OR gate and the exclusive NOR gate. Now it may also appear to you that OR gate, how did I write for OR gate? Y is equals to A or B. This is the mathematical or the Boolean representation of your OR gate. How did I write AND gate? AND gate we used to write A and B. So this one was your AND gate and your NOT gate was A equals to A complement. So this was your NOT gate. So you are quite familiar with this type of representation. Now the next thing that comes to your mind is that how to write for the exclusive OR and for the exclusive NOR. So exclusive OR gate somebody write only x, অনেকে শুধু x লেখে, so what will be the expression for this one and what will be the expression for this one? You may write simply x also, okay? So what are the expressions? This expression I will be dealing with you later on the next class or the class after that. This is my second class on digital electronics. Either on the third class or on the fourth class, I will discuss the logic output of this OR gate or NOR gate, because there is a rule called SOP, sum of product, and there is a rule called POS, product of sum. So until and unless I introduce those topics to you, so before that I will not write the expressions of XOR and XNOR. Is it clear to you? Now you may ask that why such nomenclature, নামটা এরকম হলো কেন, why exclusive OR gate and why exclusive NOR gate, right? So this will be clear to you once I write the truth table for the OR gate and the NOR gate. Let me clear all this, because these are of no use to us anymore. Okay, so once everything is cleared, just let us recall the truth table of OR gate. Okay, so I just recall the truth table of OR gate. So what was the truth table of OR gate? Just very fast we recall it. So it was simply 0 0 0 0 1 0, then it was 1 0 0, and finally it was 1 1. I made a mistake, sorry. I need to rub all this. Actually I wrote the truth table of AND gate. So this is my truth table of OR gate, and for AND gate the truth table was, so again I write A, B and Y. So I write it sidewise, you will understand it properly, that what do I actually want to mean. So here until both the inputs are high, you will not get high. That's the AND gate logic. When A and B both are high, you will get high. Now you look at the last two logics. The last two logics will play a very important role over here, and we are interested in that one only. So the last two logics. So pay attention to the last two logics, this one and this one, right? So you just pay attention on these two logics and you will find something over here. So it is 1 1 1, and then you find again 1 1 1. So you see that these two are common logics for the OR and AND gates. কোনোদিনও ভেবে দেখেছো, did you ever thought about it that this is the common logic for both the OR gate and the AND gate? Now it may appear to you that sir, the first one is also common, this one and this one is also common over here. No, we are not interested about it, because there we did not apply any signal, and it is very obvious that when you did not apply any signal, you will definitely you will not get any signal, right? So we are not interested in this one, because এখানে কোনো signal দিইনি, আউটপুটে কোনো signal পাবো না. It's very obvious logic, okay? So we are not interested in that one, but we are interested in the last logic, that is this 1 1. So we are too much interested in this particular logic, and let us try to understand that what actually this means. Now you also follow the logic in the XOR gate also. XOR gate ও same জিনিস follow করো. You follow the same on the XOR gate, and you see that there is a difference with the logics that you have studied in your OR gates and AND gates. Just look at your OR gate and AND gate, and you also look at your exclusive OR gate simultaneously. You see that in your OR gate and AND gate, 1 1 always gives you high. That is high always gives you high, irrespective of the OR operation and the AND operation. You have seen it, এটা তোমরা দেখেছো, you have seen it from your higher secondary classes, but I hope that most of you did not think of it. এটা হয়তো কেউই ভাবনি that this is a common parameter of the OR operation and the AND operation. So now it's time to think about it, that this is a common part in the OR and the AND operation, okay? And that is why the name of the gates that you see on the left hand side of your screen, বাঁদিকে যেটা দেখতে পাচ্ছ, the truth table, the big truth table, A, B, Y1, Y2, that truth table, so that is called exclusive OR gate. Why exclusive OR gate? Because you look at the first three operations of this particular operation, first three options of this particular gate. You see that the first three is nothing but it is exactly common to your OR operation. Can you see it? Okay, let me just remove this. Fine. Just concentrate on these three. Okay. So now I will be using my hand tool. Look at my this hand tool. You concentrate on this one, right? You concentrate on this box having three operations, and you concentrate on this box. That is, you concentrate on the OR box and you concentrate on the exclusive OR box. You see that the first three operations are exactly same. OR এর প্রথম তিনটে দেখো আর XOR এর প্রথম তিনটে দেখো. You look at the first three operations of OR and the first three operations of exclusive OR, you will find that they are exactly same. That is OR gate. But however, if you look at the last one, last block which I have separated out, so you see that this one, the last block is common to OR and AND. The last block is common to OR and AND. So here, that's why I will be writing over here that the last logic, this one, this last one, actually there is a sharing between the OR and the AND gate. Try to understand. এই যে লাস্ট যে অপারেশনটা, এটা কিন্তু এক্সক্লুসিভলি OR এর অপারেশন নয়. You just look at the last one. This last operation is not the exclusive operation of OR gate. মানে এটা ইন্ডিপেন্ডেন্টলি শুধু OR এর প্রপার্টি নয়. This is not an independent property of the OR gate, but this property is equivalently shared by the AND gate. Okay, so that is why this gate, this one is a circle korchi, I circle it one. This one you cannot call exclusive. Why? Because this is shared by the AND gate. Exclusive means what? Exclusive means only of that particular entity. Exclusively my pen. That means that this pen belongs to me only. But if I call pen, that pen can be shared by you and your friend. But when I call exclusively my pen, so that means it is only my pen. I will not share with you. So from that particular sense, the logic on the left side that you find, I put a tick mark. So this one is called the exclusive OR gate, because the last property is not of a OR gate. The last property is such a property. The last property is such a property which is not shared with anyone else. That is why it is called exclusive OR gate. And the circled one, this one is called simply OR gate. This is OR gate. Why? Because it shares a property with the AND gate, but this gate on the left hand side, it doesn't share property with anybody else. But the first three properties, that is 75% of the properties, are equivalent to OR gate. 75% of the properties are equivalent to OR gate. So that is why I call it OR gate, but I put an additional term that is exclusive, because it doesn't share the property with anyone else. This is a very common question at different interviews of your PG or your research, during your research. So please try to memorize this, that why the name exclusive. আমরা অনেকেই হয়তো জানবো যে it is called exclusive, the truth table is like this, the output is like this, but sometimes we miss the basic nomenclature, that why such naming is there. Okay, fine. So now I move on to my next discussion. And exclusive NOR gate, the similar logic will also work over here. So that is just the complement of your exclusive OR is the exclusive NOR. That's it. Exclusive OR and exclusive NOR has also some role to play in certain digital devices that I will definitely discuss when time comes. When there will be a dedicated class for those the devices on exclusive OR and NOR. So those have a large number of applications. So এইগুলোর application আছে, I will show you. So this is just a basic preliminary idea that the truth table looks like this, and why do we call it exclusive. Okay, so এখান অবধি যদি বুঝে থাকো, if you have understood, now I will go to the De Morgan's law now. So now I will be discussing with you the De Morgan's law. So there are two laws laws of De Morgan's. So those two laws I will be discussing next with you. Then those are the De Morgan's law. So let us try to discuss the De Morgan's law now. Let me just underline this one. So this is my De Morgan's law. So De Morgan's law has two statements, and I will write both the statements for you, and then I will try to also mathematically establish both the statements of the De Morgan's law. So De Morgan's law. Right. So the first law of De Morgan. The complement of the sum, although we call it sum, but it is actually the OR operation. The complement of the sum of variables, the complement of the sum of variables is equal to the product. Is equal to the product. Product means here actually it is the product means it is actually the AND operation. The complement of the sum of the variables is equal to the product of the complements of the individual variables. So I hope that you have understood. The complement of the sum of the variables is equal to the product of the complements of the individual variables. Okay. The complement of the sum of the variables is equal to the product of the complement of the individual variables. So this basically means that this one basically means, so let me now write it, that what does it basically means. So this one basically now means that I write the logic expression for this one. So the logic expression is, that is, let me write with a different ink, that will look better. So that is A or B or C or dot 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 complement is equals to A complement dot B complement dot C complement dot 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 dot. Right. So this is all about the De Morgan's first law. That now you read the statement ever pore dekho, the complement of the sum of the variables. What is the sum of the variables? What are the sum of the variables? What are the sum of the variables? So here the sum of the variables is nothing but this one, A plus B plus C. And then, okay, so sum of the variables is done. এই শব্দগুলো explained হয়ে গেছে. I have explained these words. And complement of the sum of the variables. Complement means A plus B plus C, and then there is a complement. Complement means an AND operation, means that you need to put a bar, a overhead bar, মাথার উপর একটা bar দিতে হবে. Done, given. That is equals to what? Equals to what? Product of the complements of the individual variable. Complements. You see that I have taken complements. A complement, B complement, C complement. What to do with those complements? We have to take the product of those complements. Product means AND operation. So this is A and B and C and dot dot dot. Of what? Of the individual variables. Individual means you have to take A, then you have to take B, so like that. So I hope that I have been able to explain you all the different words in the De Morgan's first law. Now let us come to the De Morgan's second law. So here just the product and the sum will just interchange their position. The complement of the product of the variables. The complement of the product of the variables is equal to the sum of the complements of the individual variables. So just try to understand. The complement of the product of the variables is equal to the sum of the complements of the individual variables. Now let us try to write the mathematical form of this statement, and then you will understand it properly, that what do I actually mean by this particular statement. So this particular statement actually means that, so please concentrate, this is actually the complement of the product of the variables. So first of all I take the product, right, product, a product nilam, product of what, of the complement. So put dot 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 dot, so I put a complement of this one. Fine, understood properly, product of the complement. So this part is gone. Is equals to what? Is equals to what? Sum of the complement. Sum of what? Of the complements. Of what? Of individual variables. That means A complement plus B complement plus C complement plus dot dot dot. And you believe that this is a very, very important logical tool in Boolean algebra. এটা কিন্তু অত্যন্ত গুরুত্বপূর্ণ একটা টুল. This is a very, very important tool in Boolean algebra which will help you to solve different numerical examples. এটা দিয়ে তুমি অনেক প্রবলেম করতে পারবে. Many digital devices have been designed on the basis of this De Morgan's law. Many digital devices has been designed on the basis of these laws, and there will be a many number of problems that will be also important for your examination that will be based on these two particular laws. So please try to follow these two laws. If you are not familiar with these two laws, so then please try to learn it, and if you are familiar, okay, then that's fine, so that will help you for your further studies. Next I will try to prove this law by simple logics, that is the simple truth table. This is also incorporated in your practical syllabus, that is the proof of the De Morgan's law. So let us try to show you the proof, that how can you prove this De Morgan's law by putting certain amount of signal to it. Okay. So here I start. I will take two variables over here. Proof. Let me first try to prove the first logic, that is A plus B complement. I will use two variables, and then you can extend it for more variables. So A plus B is equals to A complement and then AND operation with B complement. This is what we have learned just now. So here whatever I can do is, let me make a logic table. Okay, I have made it. What is going on? But basically I need 6 boxes, so you remember that you will need 6 boxes over here. Okay, no, 7 boxes. I need 7 boxes. Okay, so let me. Oh, what is going on? I am not going to get a straight line. 1 2 3 4 5 6 7. This mid one, let me remove this one. This is not a straight line. Now it's everything is fine, well and fine. I need 7 boxes actually. So here I will put my capital A, so then I will put this capital B, then I will put over here A plus B, and then I will write here y1. So this y1 is equals to only A plus B, that is actually A or B, and then I will write over here A complement. I will take over here B complement, and then I will write over here. So this one I will write y2, and this y2 is equals to my a and b whole complement, right? And over here I draw another line. This is the separator. Yeah, so this one is the separator, that this is the LHS. Okay, this should be y1 is equals to a plus b complement, right? So this is the separator. So that double line is the separator between the LHS and the RHS. Now you need to take the proper combinations over here, and from that combinations you can decide that whether the De Morgan's law is established or not. So you write over here the first combination is 0 0. So if you put 0 0 over here, then what actually happens is, so 0 0, you see that this is nothing but a OR operation, right? So this column is nothing but a OR operation, so you can write it what? No, the last one I have made a mistake in the last one. This one is not AB whole complement, but it should be, just give me a minute, it should be A complement product of B complement, that is AND operation. Okay, just look at the RHS. So this is the RHS and this is the LHS over here. So accordingly you need to choose it. That's it. Okay, so come back. So 0 0, then my next possibility is 0 1, then it is 1 0, and the last possibility is 1 1. Now you see that the third column is nothing but simply an OR operation. So as it is a simply OR operation, so I can write the outputs of OR, that is 0 0 and okay, no, it is OR operation, so it is 1 1 and 1, simply OR operation. And this one is what? Complement of OR operation, basically NOR. So this is the complement. So you take complement 1 0 0 and this. Okay. This one I will take a different ink for this one. So this one I will write 1 0 0 and a 0. That's a complement. And now you come back. So here A complement will be how much? A complement will be, the first was 0. So it is just compare with this. A complement will be 1 1 0 0. What about B complement? B complement will be 1 0 1 0. That's fantastic. And now you take the product of this A complement and B complement. Product means actually the AND operation. You just take a AND operation of A complement and B complement. So that should be 1, then it's a 0. I take the AND operation, it's a 0 and it's a 0. Fantastic. So now you please concentrate. Just on the okay, just give me a minute. So you just concentrate on the green inks now. So if you just concentrate on the green ink, that is the 4th column and the 7th column. So you concentrate on the 4th column and the 7th column. So you may just conclude that. Therefore, you will conclude that y1 is equals to y2, right? So y1 is equals to y2, and hence the first law of De Morgan's is proved. So are you able to understand? You just concentrate on the 4th table and the 7th table. If you concentrate on these two tables, then you will definitely understand that your De Morgan's law has been proved or has been established. The first law has been established. So now I will just basically move to my second law. I think that you can definitely do it yourself, but just due to the sake of completeness of the class, I will help you for the time being, because there are many problems that you need to do yourself. So I move on to the next proof. What is my next proof? So this is my next proof. The next proof is A B whole complement, that is equals to A complement plus B complement. So that's the next proof. So you see that in the two laws of De Morgan's, just the AND and the OR operation has changed their position. Basically AND or OR operation, that is the multiplication and the sum, they have interchanged their positions, otherwise they are completely the same. Okay, so I hope that you have definitely understood all about these ideas, and now I will go to some extended, so just I need to prove it, so I directly go to the proof of my De Morgan's second law. So let me take that table once again. Okay, so I take the table once again, and you remember I need to get 7 columns from here. First one, second, the fourth one I need a separator. There should be double line. So at the very beforehand I draw the two lines. The double line fourth column, and then I go for the fifth one, the sixth one, and the last one. That's the seventh column. And the other space I don't require, so I just remove the other spaces. So it's fine till now, and you draw a horizontal line. For the first one I need A, then I need a B, then you understand you need a product B, then I need a y1. So this y1 is nothing but A and B that complement. Then I need another A complement, I need a B complement, and finally I need a y2, which is A complement plus B complement. So that's it. And I need to show that my fourth column and my seventh column are equivalent. So that is what you need to show. So this is your, as usual, 0 0, then it's a 0 1, then it's a 1 0, and finally it's a 1 1. It is an AND operation. It's an AND operation. So for an AND operation, this is 0. This is 0, because in AND operation you will get high only when both the inputs are high. Then it's a complement of this one, so it is 1 1 1 and then a 0. Then you have a complement. So what is this A complement? Well, A complement ki hobe? What will be the A complement? The A complement will be 1 1, and then this will be 0, this will be a 0. What will be the B complement? It is 1 0 1 0. Fine. And what will be A complement or B complement? So eta OR operation korle 1 and 1 gives it high, 1 0 will also high, 0 1 is high, and 0 0 will give you 0. So I hope that you have understood definitely, and you just look at your fourth column and the seventh column. I should have used a different ink, but I forgot to use a different ink, so I highlight it in a different way. So just I put this mark, and over here I put up this mark, right? So I hope that now you have definitely understood. You just look at your boxed columns, that is the fourth and the seventh column, and from here you will definitely come to the conclusion that y1 is now equals to y2, and hence your De Morgan's second law is also well established. De Morgan's second law is also well established now. Okay, so once you have been able to establish your De Morgan's first and second laws, now you can move on to some other issues also. So the other issues that I will be discussing in this class is the universality of the NAND and the NOR gates. So let us now move on to the universality of the NAND and the NOR gates. So first of all, I will show you that NAND gate as a universal gate. So let me show you that NAND gate is definitely a universal gate. So NAND gate as a universal gate. So this is my next topic of interest now. That is, this actually means that if in your laboratory you have an AND gate, then you can construct any gate with the help of this particular NAND gate. So this is what we basically mean by NAND gate as a universal gate. Okay, so now let me show you that how can you take this NAND gate as a universal gate. Okay, how is it possible? First of all, I will show you about NOT. This is the first that you should learn, NOT. It is how to construct This doesn't look good. Not. Okay. So I will first of all show you that how can you construct a NOT gate with the help of a NOT gate with the help of a NAND gate. So you just concentrate. I will also prove you that how is it possible. So this is my NAND operation. Okay. NOT operation means 1:1. That is one input and one output. So that is why you see that since it is a NOT operation, and you know that in a NOT operation there is single input. NOT operation means ki y equals to a complement, single input, single output, or and these gates can take multiple inputs, but NOT gate will take only single input. So you see that the single input has been bifurcated into two parts. That is, A is now sent over here. You have sent one of the parts of A over here and another part over here. And that is why if this is a NAND gate, what will happen at the output? Bolo, the output ta ki hobe? What will happen simply at the output? So simply what will happen over here is y equals to, it's a NAND operation. So you may write y and then a complement. Can you eta korle? Because both of the inputs are what? Both of the inputs are A over here. So that is why A. And why the complement? Because of this bubble in front. Samne bubble ache, that means what? So this is a NAND operation. So that is how now you have to know that this y, that this A and A will definitely make you what? So this A and A will definitely give you a complement. So how do you understand this? Eta ki kore bujhle? যদি ধরো a এর ভ্যালু যদি 1 হয়, if the value of a is 1, if the value of a is 1, you just remember the truth table of your AND gate. Truth table of AND gate কি শিখেছিলাম? 1 and 1 always gives you 1 and 0 always gives you 0. তাই তো a and a মানে কি? What does this mean? That both the inputs are same. And in digital or in binary or in Boolean algebra, there is only two possibilities. A এর value কি হতে পারে? In Boolean algebra, the value of a is only two possibilities. That is, either it can be 1 or it can be 0. So if it is 1, then 1 and 1 always gives you high, and 0 and 0 always gives you low. So that's it. So this is the simple idea over here. So you see that it will be simply a. 1 and 1 korle ki pabe? If you take 1 and 1, you get what? 1. That means what? The value of a. And if you put 0 and 0, then you get 0. So that means the value of a. So that is why you can simply say that a and a always gives you a. Okay, এটা মনে রাখো, a and a always gives you a. At the same time, একই রকম ভাবে কিন্তু a or a করলেও কিন্তু you will get a. Why? Because OR অপারেশনে বলা হয়েছে 0 and 0 will give you 0 and 1 and 1 will also give you 1. So that is why, আর এটা তো একটু আগেই বলেছিলাম sharing. Just now I have discussed about the sharing of the two truth tables. Just to go back. এই যে you see that 1 and 1 মানে এইটাকে এই দুটো যা হবে আউট, if the two inputs are same, then the output will also be the same. So that's the simple logic. এখানেও তো if the two inputs are same, the output will be the same. For the first row, for the last row, এটা last row, and also for the first row, that is this particular row also. So I hope that you have definitely understood that why a and a is always a, and why a or a is also always a, right? So let me remove all this. I don't need. Now you look at the output. So what is the output? You get what? The input is a, and what is the output? Input is a, but what is the output? Output is a complement. So that means it is a NOT gate. বুঝতে পেরেছো? And this structure is very important. That single input is bifurcated into two, and then that gives you a NOT gate. I hope that you have definitely understood it. Okay, the next one. So I will go to the next one now. Next one, I don't put the name at the very beginning. First of all, let me draw the gate, and then we will decide that what gate it is. I take two such structures now. This one, and I draw a similar structure again. I draw a similar structure again. I cannot use anything other than NAND gate. শুধু NAND gate use করতে হবে, nothing else. And now let us see that what type of operation is this particular arrangement. So this is A, this is B. So definitely এই স্ট্রাকচারটা এখনই শিখেছিলে, just now you have learned that this structure is nothing but A complement. Similarly this structure will be B complement. Just if you compare with this number A structure, so এটা A complement, এটা B complement. So what will be the output now? So just you look at the output. So the output is what? It is A complement dot B complement and the total complement. Why? Because এখানে ইনপুট গুলো কি? These inputs are what? A complement and B complement. So that is the AND operation, and then there is a complement. Why complement? Because it is the NAND gate. এবার De Morgan's law apply করো. According to De Morgan's law, what is this? De Morgan's law apply করো. You apply the second De Morgan's law. ওখানে কি বলেছে? A into B gives you A bar plus B bar. A into B whole bar gives you A bar plus B bar. So if I use the second law of De Morgan, then what will happen? So এখানে already একটা bar আছে, so there will be double bar, and then for this B bar it will be double bar, and double bar makes it the original number, because if it is 1, if you take a single bar, ধরো 1 আছে, if you take a single complement that will be 0, and if you take again complement of the 0 you will get back 1. Means আমি এইটা বলতে চাইছি, I want to say this, that is 1 এর যদি complement now you get it to be 0, 1 complement is 0, and again 0 complement gives you 1. That is you get back the original number after 2 complements. So that is what is used over here. Now you look at this, y equals to A plus B. So y equals to A plus B is what? Y equals to A plus B is what? So it is a OR operation. So definitely you have answered by the time that this is a OR operation. Okay. So I remove all this because these are not essential now. So this is my y on second, and here I put it to be. So now I put the heading over here. So it is now number B, and this is OR operation. So I hope that you have definitely understood that this one is your now OR operation. Is it clear? And the last one that is left with us, that one is the last operation that is left with us is the AND operation. Universal gate means that all the basic operations. So what are my basic operations? The basic operations are my definitely the NOT, OR and the AND operation are called the basic operations over here. So now let me show you the another and the last one, that is C, and that is the AND. So this one is my AND operation. So I will show you that how does the AND operation can also be generated with the help of this particular NAND gate. So here the idea is this type of idea. This is my A, and these are the joint signals. This is my B, right? So you understand that if it is a NAND operation over here, so what actually happens is so you understand that from this structure that this is a complement. I think that I made a mistake over. Oh, I draw the same thing. Sorry, I made the same thing once again. It is not like this. দাঁড়াও, আবার দেখাচ্ছি। Okay, this is my NAND gate. I take two inputs A and B. এই যে এখানে টাচ হয়নি, you see that I didn't touch it over here, so these will decrease your marks at the time of exam. Artistic drawing is not required, but logic should be clear. Okay, and then you take this structure. I hope that this will help you to get the AND gate. Try করে দেখি, let us try it. If it works, it's fine, otherwise I need to do it again. No need to make it so longer, this will reduce the space. Okay, that's fine. So you see that what is this part? So this is simply A plus B, and then what? Complement? No. A and B complement, sorry. This is A and B complement. Understood? This is A and B complement. বুঝতে পেরেছো? A and B complement. Why? Because this is A, this is B, and this is a simple NAND gate, so A and B complement. And now this structure, এই স্ট্রাকচারটা মানে কি? This structure is nothing but a NOT gate structure, this one. So that is why at the output you will get what? You will simply get A and B, that is complement, and then again another complement, because it is the NOT gate structure. এটা তো জানি, this is the NOT gate structure. So that is why you get over here simply A into B, and that is what? A into B or A and B. So this is simply an AND operation. So you see that this is how you can construct a AND gate with the help of the NAND gate. and this is why we call the NAND gate as an universal gate, because from the NAND gate you can construct all other fundamental gates, and that is why I call it a universal gate. And now I come to the last part of my today's lecture, that is NOR gate as a universal gate. So this is the last part of my today's discussion, so I will go to that now. So the next topic, the next and the final topic of today's discussion is that NOR gate as a universal gate. Okay, it's in fine. The first one here also that I will do is I will go for a NOT gate. I will go for the NOT operation at the very beginning, and you will see that the structure is same. So as it is a NOR gate now, so I will draw a NOR gate over here. NOR gate means just the complement of OR gate. I put a bubble. The structure is same. ভালো করে দেখো, same structure হবে. It is the same structure, and this is your NOT operation. So the NOT operation is the basically same structure. Now why? I will definitely show you, because it is what? It is a or A, because এটা তো NOR operation, তাই না? NOR operation means what? OR operation, and then there will be a complement. So this is what we have done, and A plus A complement is definitely that will be A complement, because I have just now shown you that A and A is always A, and A or A, that is always A. And this you can verify from the truth table. You can verify it from the truth table of the OR and the AND logics. Okay, the next one will be the next one. I will draw it first, and then I will try to name it. Because I remember the structure, but I don't remember that which structure corresponds to which particular gate. So that is why first of all I will draw the structure. Same type of skeleton, okay? Same type of skeleton as in the NAND universality. So I draw the same structure once more. Fine. NAND-এও তো এরকম structure করেছিলাম. In the NAND operation I have also drawn the same type of structures. So this is my NOR. Now let us check bit by bit that what actually it has. So these are my NOT gates. So this will be definitely a complement, because এটা তো NOT gate. Just look at your A, you will understand. This is also a NOT gate, so this will be B. So here you have A and B complement as the input. তাহলে আউটপুটটা কি হবে NOR gate? So definitely it's a NOR gate. তাহলে ইনপুট কি ছিল? Input are my A complement and B complement. So I take the OR and then I take a complement. First of all, I take OR and then I take the complement. Why? Because it is NOR, and now I apply the De Morgan's first law, which was if there was a plus in between, so then that will be complemented, individual variables will be complemented, and the symbol will be changed. De Morgan's law, মনে রাখার সহজ উপায় হচ্ছে, the simple way to remember the De Morgan's law is if the sign is plus, then it will change to dot. Okay, plus symbol will change to dot, and individual variables will be complemented. আর যদি ডট থাকে, if there is dot, so then it will change to plus, and the individual variables will be complemented. So that is simply the De Morgan's law. So এখানে আমি De Morgan's first law use করেছি. I have used the De Morgan's first law, and you very well know that double complement means what? Double complement means actually no complement. So means the original number. So that is why you get A and B. So that is why here you can write that. তাহলে এখানে কি লিখতে পারি আমি? So definitely I can write it to be AND operation. So it is AND operation. Fine, fantastic. Now I move on to my next discussion, and here I write. So whatever is left with me, whatever is left with me is now the OR operation. So in order to perform this OR operation, let us now go forward. So here I have this structure, same structure as like the NOR gate. The NAND gate. So these are my inputs. One of the input is A, another input is B. So over here the overall input over here will be, so this is another one. So you will find over here that here it is So what will be the output at this particular point? The output at this particular point is A plus B complement, because it is a NOR operation, and you know that this particular structure is what? NOT. এখান থেকে এইটুকু structure কি? What is this structure? This is basically a NOT gate. Just to have a look over here. So this one is just a NOT gate structure. So as it is simply a NOT gate structure, so you can write it to be Y equals to, NOT gate means it will be complemented. So already there was a complement, so it will be now double complemented because of the presence of this NOT gate. And double complement means you get the original variable, that is A plus B. And so you can safely call it to be the OR operation. So that is how I have been able to show you that how does a NAND gate and NOR gate acts as an universal gate. Just you look at the skeleton has just changed over here. Look at the second one of the NAND operation. Eta to NAND er operation chilo, this was the operations corresponding to NAND, right? Eta NAND er operation chilo. Look at this one was the OR operation, and the skeleton was this, the three NAND gate structure. And now you look at over here also you see that the skeleton is same, that is the 3 NOR gate structure, but this one has changed now. So OR in the previous case has now become AND. ভালো করে দেখে নাও, same structure আছে, but নামটা চেঞ্জ হয়ে গেছে. Same structure, but OR has become now AND. And similarly you look at this double structure, this one OR gate, double structure OR gate has now become this double structure AND gate over here. So the OR and AND, just the skeleton is same, just the nomenclature is different. Same skeleton, different nomenclature you may make OR gate and NOR gate and the NAND gate. And basically I get confused about it. আমি এটা মনে রাখতে পারি না, and that is why আমি যেটা করি, whatever I do is that I first draw the gates, I first draw the structure, get the output, and then I write it that what gate is it. বুঝতে পেরেছো? And I also suggest you the same. You remember the skeletonটা মনে রাখো. One of them is 3 input gate and another is 2 input gate. You make the skeleton, get the output, and once you get the output, then you write the heading of it. আগে যদি হেডিংটা লিখে দাও গন্ডগোল হতেই পারে. So it may be different if you put the heading first. Just you put OR and then you will see that the structure is AND. So then better not to cancel. So better will be you get the output and then you put the heading. So I think that this much is sufficient for this class of our digital electronics. That's the second class. So I will be ending up my class over here. So please get prepared, and thank you for your kind attention.